Today we're going to talk about acid-base reactions, and let's jump right to it. So we have our definition. Now this is going to be kind of one of the definitions we talk about for acids, but it's not the only definition that we're going to talk about for acids. So our definition is going to be an acid is something that ionizes to release hydrogen ions into solution. Now, like I said, this won't be the only definition we use for an acid. So let's talk about these guys real quickly here. So here's an example. Let's say we have HCl gas being bubbled through water. And what would be the product? Well, what's going to happen is the HCl gas will ionize, and we will get hydrogen ions in solution. And we're also going to get the chloride ions in solution. And you can see that these are aqueous, and that takes care of the water that we're dealing with. Now, this hydrogen ion here we also call a proton, because essentially a hydrogen ion is a hydrogen atom that has lost its electron, and all that's left is its proton. There's no neutrons available. So we sometimes call an acid a proton donor. Proton donor looks like an H. Proton donor. So, and we could often identify an acid by just looking at the formula. And typically, if it starts with a hydrogen, although not always, if we have a hydrogen on the front, there's a good chance that it might be an acid. And I know you might be thinking, hey, water's got a hydrogen on the front. And water can act as an acid as well, but it can also act as a base. We'll talk more about that later. Okay, but think in terms of if you have a nonmetal ion, whether it be just a nonmetal ion like chloride, bromide, iodide, or a nonmetal ion like a polyatomic like nitrate or sulfate, I think it's probably going to be an acid if we throw a hydrogen on the front. And so let's talk about real quickly what a monoprotic acid is. It's going to be an acid that has the ability to ionize a single hydrogen ion, and a good example of that is the example that we gave right there. HCl ionizes just one hydrogen ion per molecule. A diprotic acid is going to be an acid that can ionize 2 hydrogen ions per molecule, although they don't do it equally. And so a good example of this would be H2SO4. So if we took some H2SO4 aqueous and we put it in water, you had a solution, what essentially what's going to happen is we're going to ionize. You see that there's a possibility of ionizing 2 hydrogens. So you're going to have 1 hydrogen coming off, and what will be left is a hydrogen, so 4, with now a 1- charge. So that's the first hydrogen coming off. And this will ionize completely, 100%. Complete ionization. And then what's going to happen is we can take this HSO4 1-, and that one will ionize HSO4 1- into the hydrogen ion and leaving the sulfate ion. And this is a 1- here. Let me erase that real quick here. And these are both in aqueous solution. Now, when this happens, this is incomplete, meaning it's less than 100%. So if we were to model this in a beaker, what we would see is when we put some H2SO4 in there with some water, we're going to see some hydrogen ions floating around. We're also going to see some HSO4 1- ions, and we're going to see some sulfates floating around there as well. All 3 of those will be present, but they will not be present in equal numbers. We're probably going to have more hydrogen ions present. Another definition that we're going to kind of modify as we go through here, but we'll start off with a simple definition of a base. It's going to be a compound that produces hydroxide ions that can react with hydrogen ions. We also say that they can accept a hydrogen ion. And so let's give you an example of a base. So sodium hydroxide, we see that hydroxide on there, hydroxide ions. So let's take some solid sodium hydroxide and we'll throw it in water. And what's going to happen is we're going to get ionization occurring. And so we're going to get sodium ions plus hydroxide ions in solution. That's going to take care of the water with the aqueous. And so this is going to give us our hydroxide ions, which are basic. If we remember from our general chemistry, acidic solutions tend to be less than 7 on the pH scale. Basic solutions tend to be greater than 7 on the pH scale. Okay, we have to also remember what happens sometimes with some of our bases that are still strong bases, as we'll learn about here in a little while. Like calcium hydroxide, if we took some calcium hydroxide and we threw it in water, same thing is going to happen. It's going to ionize into the calcium ion plus the hydroxide ion, aqueous on both of these. But one thing we have to remember, because we have an alkali metal here, which has a 2+ charge, we have 2 hydroxides per molecule. So we're going to balance this with a 2 here. And so that's just something to keep in mind when we ionize alkali and earth metal hydroxides. They're going to have a 2-to-1 ratio off of the metal ion that they're using, whereas an alkali metal like sodium is only going to have a 1-to-1 ratio. What I want to do now is I want to identify the difference between strong acid and base and a weak acid and base. And this becomes important in chemistry for a couple of reasons. One is in writing net ionic equations, they're treated differently, strong acids and bases, and weak acids and bases are. And then we get into equilibrium later on in this class, which we spend a lot of time looking at weak acidic solutions and weak basic solutions. So let's talk first off about a strong acid. A strong acid is going to be an acid that ionizes, we say 100% of the way, or completely ionizes. And what this means is, let's say we have an example of a 1 molar HBr aqueous solution. What's going to happen is that is going to ionize into 1 molar of the hydrogen ions plus 1 molar of the bromide ions. Complete and total ionization there occurring. So that's really important. Now, there are 7 strong acids that we need to know. And we need to know the names of them and the formulas of them. So here are our 7 strong, and we'll put down the formulas first and then we'll do the names of them second. Okay, so here's our 7 strongs. We have hydrochloric acid first. And so that naming convention is going to follow through with the next 2. So the hydrochloric, hydrobromic, hydroiodic, and then we have nitric acid, deriving its name from that nitrate ion there, sulfuric acid, we have perchloric, and chloric acid. Okay, so those are all our 7 strong acids, and so the important thing to remember about 7 strong acids is they ionize 100% of the way. So again, if I asked, if you had a 2.5 molar HNO3 solution, what is your concentration? Concentration denoted by brackets of your hydrogen ion, it's going to be 2.5 molar because there's 100% ionization going on there. Let's talk about what the difference between this and a weak acid is. And so a weak acid is going to be less than 100% ionization, and often it's pretty low, anywhere from 5%, maybe a little bit more than 5%, and a lot less than 5% on the weak side. So an example of this would be an acid that is especially nasty, which is hydrofluoric acid, although there is a small amount of ionization occurring. So hydrogen ions plus fluoride ions. And really what's happening here is we do get an equilibrium occurring, and we'll spend a lot of time talking about equilibrium, denoted by an arrow. And so really what's happening here is the concentration of the HF in a solution is going to be great, but the concentration of the hydrogen ion and the fluoride ion are going to be, a lot less. We would say that this equilibrium definitely lies to the left, and we'll get more into what that means. But it really does mean that when you put HF into a solution, it really doesn't ionize 100% of the way, which makes it a weak acid. And so you might be thinking, how do I tell the difference between a strong acid or a weak acid? And here's the key. So if the acid is not strong, which is, there's 7 strong acids by default. So again, if the acid is not one of the 7 strongs, all others are weak by default. So any other acid other than one of the 7 strongs, we just consider weak acid. So a real good example of that is acetic acid, derived from that acetate ion. This is the acid that is present in vinegar, and it's considered a weak acid. You can put it on your salad or something like that and eat it, no problem at all. Weak acid, real low ionization, like 5% ionization or something like that. Okay, on strong bases, bases are going to be, as we said before, something that donates or accepts a hydrogen ion but donates a hydroxide ion. And so the bases that we are dealing with for strong bases are going to be our alkali metal ions plus the hydroxide ions, and also our calcium ion, our strontium ion, and our barium ion. These are going to be our strong bases. Again, we get 100% ionization on these. So if we have a 1 molar solution of sodium hydroxide, we are going to have 1 molar sodium ions, and we're going to have 1 molar hydroxide ions as well. Okay, and that's a strong basis. So let's talk now about weak bases. Well, weak bases are going to be less than 100% ionization. Okay, and so good examples of our weak bases are going to be everybody else other than alkali plus calcium, strontium, barium. So real good candidates for the weak bases would be the beryllium hydroxides of the world and our magnesium hydroxides. But we also throw into this category, things that aren't necessarily donators of the hydrogen or the hydroxide ion, but they are acceptors of hydrogen ions. And a good example of that is ammonia. Ammonia doesn't have a hydroxide, but it will definitely accept a hydrogen ion when placed in water. And when it does that, it turns into the ammonium ion, and it leaves a hydroxide left over. So ammonia is basic because the product of its reaction is a hydroxide. Now, we had previously talked about neutralization, or excuse me, we had previously talked about net ionic equations, so with respect to net ionic equations, what do we ionize when it comes to all these other types of reactions that we haven't talked about? We talked about double replacement reactions, but here's the list of what to ionize, and then we'll talk about a list of what not to ionize. So what do we ionize? Well, I always ionize, as we talked about before, soluble compounds, and we apply our solubility rules to those. So alkali metals, nitrates, ammonium, acetates are going to ionize. Remember, there was that exception with the acetates. We also like to ionize strong acidic solutions and strong basic solutions. And we just talked about our 7 strong acids, and we just talked about our group 1A plus hydroxides, and our Cassava plus hydroxides as well. Those are our strongs. Okay, that's what we ionize. Now, what do we not ionize? Oops, ionize. So these are the things that we are not going to ionize. We're not going to ionize weak acidic solutions. So once again, if you're not one of the 7 strongs, you're weak. Weak bases in an ionic equation, we do not ionize them. We also don't ionize a few other things. We're not going to ionize water, pure liquids. We don't ionize water. We don't ionize gases. So a good common gas is like hydrogen gas that can produce, and we'll talk more about some of these gases, or some carbon dioxide gas or something like that. Don't ionize gases. And solids. So if we drop some solid magnesium or some solid magnesium hydroxide into a solution, we are not going to ionize those types of things, okay? So let's keep these rules in mind as we go forward on some of the other things that we're going to talk about. And so we're going to get into the idea of neutralization reactions next. And a neutralization reaction is a solution, as we see, that is produced when we mix an acid or a base, all right? And the products of a neutralization reaction are typically what we call a salt plus water. And a salt can be any ionic compound. It's not necessarily just table salt, NaCl. It could be KCl in any case or something like that. Okay, so let's take a look at an example of a neutralization reaction, and you'll see why it's neutralization reaction. Let's say we have 20 milliliters of hydrochloric acid, and let's say this guy is a 0.25 molar solution, and we're going to mix it with 20 milliliters of potassium hydroxide, as we said before, 0.25 molar solution as well. So we're going to write a couple things. We're going to write a complete molecular equation. We'll call that complete molecular equation, and we're going to also write a net ionic for this. So complete molecular equation. We have HCl aqueous plus potassium hydroxide aqueous. And this, we're going to treat this as a double replacement reaction with potassium and hydrogen, just kind of switching places. So we're going to form potassium chloride, and we're also going to form water, H2O. Essentially, we're forming HOH, which is really just water. Okay, now water is going to be a liquid. Now we apply our solubility rules to potassium chloride. It's got an alkali metal in it, so it's going to be aqueous. Now, what we can then do is we can write a complete ionic equation. I'm just making up these little abbreviations, complete ionic equation now. So we're going to ionize everybody who is soluble or is a strong acid or strong base or something like that. So HCl, we know, is one of the 7 strong acids, so we're going to ionize it. So we're going to write hydrogen ion plus the chloride ion. KOH is our strong base, so we're going to ionize K plus the OH. We said potassium chloride is soluble because of our solubility rule, so potassium plus chlorine, or the chloride ion rather. And then water, we do not ionize because we said previous rule that we do not ionize water. So now we can identify our spectator ions, and we always want to cross out our spectator ions in our net ionic equation. So let's cross out our spectator ions. So spectator ion of chloride, spectator ion of potassium, and so what we are left with is we're left with a hydrogen ion plus a hydroxide ion yields H2O liquid. So we call this reaction a neutralization reaction because essentially if we have equal amounts, and we had equal amounts of equal molarity acid and base, we use up all of our hydrogen ions and we use up all of our hydroxide ions, and all we do is we produce water. And we happen to produce potassium chloride salt as well, which does not affect pH. So potassium and chloride do not affect pH. So essentially we've brought the pH back to 7, having a strong acid and strong base mixed together. Okay. I want to give one last example just because this example has some curveballs in it. And so what we're going to do is we're going to write a complete molecular equation, and then we're going to write a net ionic equation, net ionic. And so we have 1.5 molar acetic acid solution being added to solid magnesium hydroxide. So a couple things we really need to pay attention to. We do have an acetic acid solution, but we do know that acetic acid is a weak acid because it's not one of the 7 strongs. We also have solid magnesium hydroxide, and we identify solid because it's a solid, and that's we need to know that, especially for a net ionic equation. So for the complete, we're going to write acetic acid, which is the acetate ion with the hydrogen popped on front. And I'm going to write it as aqueous, but that's kind of misleading. We'll talk about that in a moment. Solid magnesium hydroxide, so magnesium hydroxide. And double replacement neutralization reaction occurring here. So we're going to get magnesium acetate in the aqueous form, and we are going to get water in a liquid form. Now, there's our complete molecular equation. Now, do we ionize? So the answer is we do not ionize here because this is a weak acid. So I'm going to go ahead and write this down here as HC2H3O2 in my net ionic. Do we ionize here? The answer is no, because this is a solid. So I'm going to go ahead and rewrite it, MgOH2. Do we ionize the magnesium acetate? And the answer is yes, because this is a soluble Mg2 plus C2H3O2 1 minus. And last but not least, we don't ionize water because it's a pure liquid. Okay, and then we can be asked the question: Do we have any spectator ions? And the answer is no. No spectator ions. Nothing gets crossed out in this case. So our neutralization reaction occurs this way. Q, and I'm going to go ahead and put some state symbols in here, AQ, AQ, and liquid. Okay, so there we go. And the last thing I just have to do is I throw a balance here. So I'm going to put a 2 here, a 2 in front of my acetate, 2 in front of my water, just to balance everything all out. Okay, that's the end of the video for tonight. Acids and bases, strongs and weaks.